You remember algebra class, right? All those X's and Y's, the weird symbols. Well, what if I told you there's a secret language hidden inside those equations? That something as common as a polynomial is actually trying to tell you a story through its very structure?
That's exactly the question we're diving into today. We're going to peel back the layers on one of the most fundamental things in algebra and find this really elegant and visual story that's been hiding in plain sight the whole time. So, our mission today is to crack this code. And by the end of this explainer, you're not just going to know what a polynomial is, you'll actually be able to read the stories they're telling.
All right, first things first. We got to meet our main characters here. So, what is a polynomial anyway? Okay, the easiest way to think about it is like building with Legos. You've got your X bricks, those are the variables, and you've got your plain old number bricks, which we call coefficients. You can stick them all together using addition, subtraction, multiplication, pretty much anything. But there's one really big rule. The powers, the exponents, they have to be nice, whole, positive numbers. No weird fractional bricks allowed.
Think of this like a bouncer at a club. On the left, you've got the legit polynomials. They're on the list, they get in. But on the right, these are the rule breakers. Square root of x? Nope, that's really x to the power of 1/2. That's a fractional power, so you're not getting in. And what about 1 over x minus 1? That's division by a variable. That's a big no-no. Sorry, you're not on the list either.
Now, we can sort these guys by their degree, and that's just a fancy word for the biggest exponent you see. So degree 1 is called linear, degree 2, that's a quadratic, and degree 3 is a cubic. These are the big three we're really going to focus on.
Okay, now for a really important concept, the zero of a polynomial. Think of it like a magic key. It's a special number that when you plug it in for x, the whole expression just, poof, turns into 0. It just works. For example, if you have x squared minus 4, what happens if you plug in 2 for x? Well, you get 2 squared, which is 4, minus 4, and that's 0. So, boom. 2 is a 0 of that polynomial. So we have this idea of a 0 from an algebra perspective, but what does it, mean? What does it look like? Well, the first big clue isn't in the numbers at all. It's in a picture.
Let's totally shift gears for a second, from algebra to geometry. If we were to actually draw a picture of a polynomial, graph it, where would these zeros be hiding? What would they even look like?
All right, here's our first big piece of the code. Remember the degree, that highest exponent? It gives us a huge clue. It tells you the absolute maximum number of zeros a polynomial can have. So a polynomial with a degree of, say, n, can have at most n zeros. That's the rule.
Let's start super simple. A linear polynomial. It has a degree of 1, right? So its graph is just a straight line. And look, it crosses that main horizontal line, the x-axis, in exactly one spot. That's it. That's its one and only 0.
Okay, let's level up. A quadratic polynomial has a degree of 2. Its graph is this cool U-shape called a parabola. Now, our rule says it can have at most 2 zeros, and if you look at this graph, you can see it plain as day. The curve dips down, crosses the x-axis, goes back up, and crosses it again. 2 spots. Those are its 2 zeros.
But that phrase, at most 2, is super important. A parabola doesn't have to cross twice. It could just swoop down and kind of kiss the x-axis at one single point before turning back around. In that case, it just has 1 zero. And there's even a third possibility. The parabola could just float entirely above the x-axis or entirely below it, never touching it at all. And if that happens, it has no real zeros. So for a degree 2 polynomial, you can have 2 zeros, 1 zero, or none. But never more than 2. The rule holds. And this pattern just keeps on going. Check out a cubic polynomial, degree 3. Its graph is this cool, wiggly curve, and it can weave its way across the x-axis up to 3 times. So, you guessed it, a cubic can have at most 3 zeros.
And this is the big secret we've been hunting for. Those zeros we talked about in algebra, they are the exact same thing as the points where the graph hits the x-axis. That's the connection. The algebraic answer is the geometric location. It's all one and the same.
Okay, that is super cool. We connected the numbers to the picture. But drawing a graph every time? That's kind of slow. So what if there was another way? This brings us to the final piece of the puzzle, a really powerful shortcut.
I mean, graphing is great for understanding what's going on, but it's not always practical. So is there another secret? a code hidden inside the equation itself, in those coefficients, that can tell us about the zeros without ever having to pick up a pencil and draw?
You bet there is, and here it is. For any quadratic, ax squared plus bx plus c, there's a direct link between those numbers, a, b, and c, and the zeros. Get this. The sum of the two zeros will always be negative b divided by a. And the product of the two zeros will always be c divided by a. It's like a cheat code for algebra. Don't believe me? Let's try it out. Take x squared plus 7x plus 10. So a is 1, b is 7, and c is 10. According to our code, the sum of the zeros should be negative b over a, so negative 7 over 1, which is just negative 7. And the product should be c over a, which is 10 over 1, so 10. Now, the actual zeros for this thing are negative 2 and negative 5. So let's check. What's negative 2 plus negative 5? It's negative 7. And what's negative 2 times negative 5? It's positive 10. It works perfectly. The code is real.
Okay, let's zoom out for a second. We've just cracked a couple of pretty big secrets about these polynomials. So, what's the big takeaway here? Why does this even matter?
So, what did we figure out? We now know that a polynomial's degree gives it its name, linear, quadratic, and tells you the max number of times its graph can hit the x-axis. We found out that those hitting points, the zeros, are the same thing as the graph's x-intercepts. And we cracked that awesome secret code that lets us find the sum and product of those zeros just from the coefficients.
If you remember just one thing from all this, let it be this. The zeros of a polynomial are literally the x-coordinates of the points where its graph crosses the x-axis. That's it. It's this beautiful, perfect bridge between the world of abstract algebra and the visual world of geometry.
We started off by asking if equations could tell a story. And it turns out they absolutely can. It's a story about shapes and intersections and these incredible hidden patterns. So now that you know the secret language of polynomials, what other stories are out there, hiding in the numbers, just waiting for you to find them?